All right, hi everybody. This is the worksheet 7 worksheet on electromagnetic induction. I'm trying out a new setup here with this recording of the paper so you guys can see as I write. It seemed like based on the evaluations, sorry, helicopter going over right now. Based on the evaluations, it's easier to see me write and go through it and explain my process, which is totally justifiable. Like same thing with me. It's actually right now my phone, like I said, on a hydro flask, so that's not, kind of putting it together as I go. So hopefully it looks good. On my end, everything looks HD, and I pinned this video, so you guys should be able to see that. At this point, I'm just gonna write down the equations, and yeah, I'll just start with that, and then we can just all get used to what we like to see. So I apologize if I might be going slower than usual today. I'm just gonna be getting used to having this. In case you can't see it, it's basically like a water bottle right in my face. So I have to like look around. Okay. So, I mean, we're talking about electromagnetic induction. You know, this equation is going to be here. And I'll explain and talk about each one of them more as they come up. And I'll even say within each problem why we're choosing one and what tipped me off to choose a certain one. So for now, I'm just going to get everything down. Again, I apologize that this might not be what we're used to seeing, but hopefully it's not too bad. I'm just going to get rid of that guy there. I'm just going to take a quick pause and talk about that equation I just wrote. Let me see if I can grab a different color here. There you go. Being this equation. So that's a special equation, which is relative to a square or rectangle moving through a field. So like that's an example of that right here. And the reason, well, what tips me off that I can choose this one when it's only I'm talking about a square or rectangle moving through a field is that it's relative to this length, not the area. As you expect, like a circle that moves through it, the whole area is affected. But here, this rectangle, there's actually an equal and opposite effect on both sides. So you're just worried about the one length that's not. So like in this case, you're only worried about this length, right? Because these two right here will be canceling each other out. So a little note I'd write for this guy is only use this equation when you have a square or rectangle moving through an electric field. So, and that means in the case that you do see a square rectangle moving through an electric field, it's really probable that you're going to be using this equation, okay? The only other thing I want to talk about induced EMFs, so that's what that symbol represents, is the three conditions in which they come to be. So I'm going to write over here. So E induced, this is talking about the symbol. What causes them? There's three things. The first one, you might guess, is just a change in B, right? So as this rectangle moves through a magnetic field, there's obviously going to be a change there. Same property, change in area. So the area that's within B, and that makes sense. Those guys kind of work together. As less area is in B, there's going to be less field there. So it's going to be kind of checking both of those boxes. That being, it's going to be like lowering magnetic field, and the area within is going to be changing. And finally, this is kind of the most tricky one. It's a change in orientation of like a wire loop. Right? So change in orientation of loop. Okay. So that means, let's say we have a loop that's, like a circle like this in plane. If we put it on an angle, it'll actually be having the field going through it will be adjusted. How I kind of imagine that is, imagine I'm holding a cup right here and you dump water from the top. So the water goes like this right into my cup. If I put it on an angle, the amount of water that goes in isn't going to be the same amount as if it's flat. So that tells me that there's a change in B, which I said, like when you think about this, it's kind of going to be checking multiple boxes at once. There's going to be a change in orientation. There's going to be a change in B acting there. That tells me there's going to be an induced EMF. All right. The next one, we don't really use this as much, but I'd rather give it to you here in the off chance we do. And when I say we don't use it that much, that's basically me saying don't expect to use it, but I never want to be you know, like the one and say like, oh, don't expect to use it. And the next thing you know, you need to use it. That's just me playing it safe.
Sammy, just to clarify, Formula 2 NBLV, that's for when a square or rectangle moves through a magnetic field, right? Not a electric field. Okay.
Oh,
Great.
did I say something else?
I think you said electric, so I got a little.
Oh my goodness. Yes, thank you, Isabel. That's absolutely correct. I am talking about a magnetic field. That is a huge distinction. Please mark that from the record. Yes, magnetic field. I apologize. That totally I totally slipped there. That's correct. So here, change a magnetic field. That's what B represents. So if I've been saying electric this whole time, I do apologize. Magnetic field. Okay, and then this final one. Not such a popular one too, but I'd rather you guys have it. Okay, so now I've kind of established, I mean, obviously the two most important ones are these two. Those were the ones that come up that much, the most. And we can see how like these guys are all equal right here like this. And again, this one is for square or rectangle moving through a magnetic field. All right, and here are 3 reasons for an induced EMF. The next thing I want to do is take a pause from this worksheet, and I want to talk about an example because it seems like there's just been a little bit of confusion on finding the direction of an induced current. So I want to explain my thought process. So here we have this wire. I just made up this example completely random. I have this wire going on an angle and a current going this way, going down, right? Pointing that way. I also have this wire loop moving away with a velocity v naught. So essentially, we have a wire loop being pulled away from the current. Because that wire loop is getting pulled away from the current, as you can expect, the magnetic field will get weaker, right? You can, like, it will still exist even if the loop's all the way here, even if it's all the way on Saturn, but hypothetically, it's going to be so weak at that point that it's basically a null thing. So here, it's moving away, so the magnetic field in the loop gets weaker. Because the fact that B goes down, magnetic field goes down, that tells us that flux goes down, right? That makes sense. Therefore, the original B and B induced must be in the same direction. What do I say what does that mean when I say same direction? That means, you know, on this side of the loop, the field is, you know, right-hand rule, thumb in the direction of the wire, so going down, fingers curl, and they're coming out of the page on this side, right? Our 4 fingers are coming out of the page on this side. So that means B out. This original magnetic field is out. Because the flux is decreasing, that tells me that the B induced basically is also coming out. So for the induced magnetic field to come out, that is how we orient our fingers. There's only one way that can work, right? The only way for my fingers to come up is to have them like this and my thumb pointing in the counterclockwise direction, right? If I did it this way and going in, sorry, helicopter. If I do it this way, my fingers going in, look, that's clockwise. That's breaking the rule. We know they're going in the same direction. Fingers are pointing out, thumb points this way, and I know my my induced current is counterclockwise. So I hope that clears that up, like kind of my logic. Basically what I think is, okay, loop's going away, so that means field's decreasing. Because field's decreasing, magnetic flux is decreasing. Because that's decreasing, I know that the original magnetic field and the one acting within the loop are the same. Therefore, my I induced, if it's pointing that way, must be counterclockwise. All right, so that was just to frame our understanding, and let's go back to this worksheet. Here we have
I'm sorry, do you mind if I ask you a really quick question about that?
Go.
I don't really understand, like, I understand like the magnetic field move like decreasing and the flux going down, but how can you tell that it's coming out of the not in?
Yeah, so here's my wire, right? We know that with this right-hand rule, I put my thumb in the direction it's going.
Yeah.
Okay. At this point, my fingers need to curl. So it's on the same side as the wire. So originally it's curling into the page, but that's not on the same side of this loop. So I curl all the way past, and it's basically 270 degrees, and now my fingers are pointing out. B is out. Does that make sense? So my wire is,
Yeah.
imagine this is my wire, right?
Yes.
Pointing in this direction. I rotate, and my loop is on this side, right? My loop is green pen.
Yes.
Okay. Thumb in the direction of the current. My fingers curl. And then when it's on the same side, it's pointing out. Does that make sense?
Wait, what is it on the same side? Like, what are you referring to when you say it?
When my fingers are on the same side as loop. Loop is here, right?
Yes.
I'm gonna write an X where loop is. That's confusing. I'm gonna write a smiley face where loop is. Okay.
Okay.
My loop's on this side of the wire. Current's going this way. Thumb in the direction of current. My fingers curl. And now that I'm on the same side as wire, when I'm on the same side, my fingers are pointing up.
Got it. Okay.
Does that make sense?
Not kind of, not really. Wait, what do you mean? But like your fingers are pointing, you mean out?
Yeah, pointing out of the page.
Okay. Okay,
Yeah.
I got it then.
Because this is like pointing into the page, right? So this is pointing out of the page.
Right. Okay. Thank you.
All right, we're good?
Mm-hmm.
All right. Good clarification. I apologize. Sometimes I'll say, yeah, like pointing up, but I apologize. I guess I should be more clear and say coming out of the page. So I will keep that in mind. All right. So let's look at this next example. So here we have a rectangular loop. I mean, this is a word problem, but just by reading this alone, had this been like a plug-in question, I know I'm going to be thinking to use this equation. But that's not the case here. So here we have a rectangular loop being pushed to the left, where a uniform magnetic field points inward. Therefore, magnetic flux is increasing or decreasing into or out of the page. So let's just put a pause there and think about it. So because we're being pushed to the left, basically the amount of area of this rectangle that's within this field is reducing, right? The field's all right here where these X's end. So as this rectangle moves more and more this way, less field is acting through it. Therefore, decreasing. And then which direction is it decreasing? We know X is going into the page. All right. And why is it doing that? And I kind of said that already, because B inside of the, so area, I say this, B inside loop is decreasing. Less B acting on that. So we need to impose this. This is kind of where Lenz's law comes in. We want to oppose this. So we need to add more magnetic field into or out of the page. Well, it needs to go into, right? To get this field, an induced current would be produced, and then we're asked clockwise or counterclockwise. So per the fact that it's going into the page, we know that fingers go in, thumb points this way, and within this rectangle, that's going to look clockwise. So the main thing to think about here is how Lenz's law is acting. Because we are decreasing into the page, to kind of maintain an I don't know if I want to say equilibrium or to counteract, but think about it within those lines. To keep it balanced, we're going to want to increase into the page, more magnetic field into the page, right? Remember, at this point, less is going into as it moves out. So to oppose this, we want to have more magnetic field going into the page. Because it needs to go into, fingers in, point left. As it works here, that's clockwise. All right. So let's move it on to question 1B. So within 1B, we have multiple systems. We're going to see what is the direction of the induced current in the circular loop due to the current shown in each part. So right off the bat, we see I is constant. What are our parameters for having an induced EMF, a change in B, a change in A, or a change in orientation of the loop? What's changing here? Nothing. Therefore, no induced current. Okay. Differently. In this one, part B, apologize, must be hard to see, but that's an arrow pointing downwards. So we have a decreasing current. What does decreasing current tell us? That tells us we have, well, I guess let me define my direction of the B field. I guess it'd be easier for you guys to think about it that way. Thumb in the direction. I guess I'm going to start using my highlighter. Let me put a different color tip on it so it becomes very clear. Sorry, guys, I'm like building all these tools as I go. From now on, orange tip tells us the direction of current, okay? So we have a current pointing downwards and we're decreasing. So I put my thumb in the direction of the current, and my fingers curl to where the loop is. Okay, so my loop's on the left, so it curls into the page. I know my B field is going into the page. So I'm going to write, okay, B going into the page. Because I is decreasing, that tells us B is decreasing into the page. Therefore, by Lenz's law, to oppose this, we need to increase B into the page within this loop. So that means right here, we need to increase that. The only way for our fingers to be pointing inward relative to this loop is our thumb pointing, it's like pointing down, but you can imagine it's like kind of curved that way, right? Like it's not, the circle's not that big, I apologize. Pointing down like this, with our thumb pointing down. So as it acts here, this arrow pointing down, that comes out as a clockwise I induced. All right. Same thing right here. So we have an arrow, what's this one, pointing this way. Orange tips, the direction of the current. I'm going to use my right hand rule. Sorry, this is going to be tricky. I have to stand up. So I have to, I have my arrow pointing this way and my thumb lines up and I curl this way. And you can see the loop is on this side, right? Where my pointer finger is. Thumb, fingers curl. My 4 fingers are now pointing out of the page. Okay, so that tells us this guy pointing out. What's happening to this? I is decreasing, therefore B is decreasing out of the page. By Lenz's law, because B is decreasing out, we need to increase B out. So within this circle, we have another coming out of the page. The only way that works is to have our fingers curl up, thumb pointing like this, counterclockwise. Counterclockwise. At any point, if I lose anybody, please speak up. I'm always, we'll make sure to clear it up. And then let's look at example D. All right. So here, I is increasing, pointing, well, I don't know what direction, if it's mirrored on your guys' screens, but to me, it's pointing to the left. Thumb in the direction, loop is on this side where my pointer finger is pointing. Thumb, fingers curl. I see that B is pointing out of the page. Therefore, and it's increasing. I is increasing, B is increasing. Therefore, increasing B out of the page, we need to increase the magnetic field going into the page. So that means within this circle, we're going to be looking into the page. Fingers curl like this. We can see that our fingers curl into the page, thumb points that way. So as it applies here, it's going to be clockwise. And obviously this is, an I induced. All right. So those were kind of our general.
Explain the last one more time.
Oh yeah. So I have my current, oh, I'm sorry, wrong highlighter. I have my current like this. This is the direction in which it's going. My circle is on this side where green pen is. It's right here. Circle's on my wire loop's on this side. Put my thumb like this, curl my fingers. I'm now coming out of the page. My original B field is pointing out of the page. Because my I is increasing, I am increasing my B out of the page, increasing my magnetic field out of the page. So by Lenz's law, I want to oppose this by increasing the B into the page. The only instance where my fingers are pointing into the page within this loop has my thumb pointing in the clockwise direction. Therefore, the induced current is in the clockwise direction.
Okay, cool. Thank you.
I really hope I'm recording. Okay, thank God. All right, so those are our kind of framing questions, and we have a good idea of how this all acts. So excuse me for 1 second as I adjust my water bottle so I can access the bottom of this page. Okay, so let's start with part A. So what we're given here is a 16 centimeter diameter circular loop. Here, I don't want to block your guys' view, so I'm going to leave this here and I'll read from my own notes. So a 16 centimeter diameter circular loop of wire with a resistance of 5 ohms placed perpendicular to a value 5 magnetic field pointing to the right. The plane of the loop is rotated until it makes a 60-degree angle with the magnetic field lines. So the first thing we're asked is, what is the magnetic flux through the loop at this angle? So magnetic flux, right off the bat, we know what we're working with, huh? We know we're going to be using this equation number 1. So to just remember that, I'm just going to write a little 1 down here. That tells me that this is part A, we're using equation number 1. What's that equation number 1? Magnetic flux. I'm gonna move this up because it's easier for me to see this way, but hopefully you guys have that written down now. It's flux B equals cosine theta. Okay, so we know we're using that equation, but the special thing about this one is it's rotated until it makes a 60-degree angle with the magnetic lines. And we know initially that the magnetic field is pointing, we know that the magnetic field lines are pointing to the right. So we have a field line pointing to the right. Within this, we have a loop that's now rotated. I'm just going to write an axis like that, make it a little easier to see. Another one right here. These are my field lines, such that it's 60 degrees right here. All right. Now we want to know, or what we need to know actually, is this angle right here. Because remember, what does this angle represent? That's the angle between the loop, the induced current that's going through, so that's what that arrow is pointing to right now, and those field lines right there. So if you have a good eye, that's 90 degrees, 90 minus 60 equals 30, so my theta equals 30 degrees. At this point, I have enough to plug in everything. So I have my B value that's given, area of a circle, pi radius squared, and then cosine 30. So what does that come out to? That's 8.7. All right. Part A, done. That one should be this one should be good. We should be setting up that when to use this equation, that being equation number 1, and what that angle, how I'm treating that angle here. So let's move on to part B. Make sure I addressed everything I wanted to there. Okay. Part B. So now we have this loop rotated more to make a 30-degree angle with the field lines. So what does that tell me now? It's rotated 30 degrees down, so theta is just going to be equal to 60. Remember, it used to be, sorry, I need to adjust again. Theta used to be 30 degrees, but now it's 60 as we rotate to make a 30-degree angle with the field lines. This takes 5 seconds. What direction and magnitude is the induced current in the wire? I'm going to keep my equation sheet handy because in case I want to re-reference it. Okay, so again, we're going to be starting with a similar thing. Equation number 1, right? Only difference is now we have a new value to plug in for theta. That's squared right there, cosine 60. So that comes out to be 5 times 10 to the minus 3. All right. So the next thing is we are now meeting criteria for an induced EMF. Oops. We are now meeting criteria for an induced EMF. We have a change in orientation of the loop. Remember, I said that's one of the more tricky ones to catch. So now we can start thinking about how that EMF is acting. Oh, I'm sorry, I didn't even finish reading this. This takes 5 seconds. What is the direction and magnitude is the induced current in the wire? So yeah, we know there's going to be something induced, and also the change in orientation tells us. So now we're thinking, though, what equation should I be using here? Well, the first, what I like to think is, in this case, this n value will always be equal to, well, not always. In this case, the n value is equal to 1, right? It's just a singular loop. Had there been multiple loops, then n will be however many loops there are. So we know there's going to be a change in magnetic flux over amount of time. They tell us it takes 5 seconds. So we can just use this equation, this part right here. as you know, we just solved for that guy. So now I'm going to use equation 2. So my induced EMF, the change in flux. So that being from part A to part B. And like I said, n equals 1. What was our flux in part A? That was 8.7 times 10 to the minus 3, close parentheses, minus what it is now, 10 to the minus 3. That's what we just solved for. And what was the change in time? 5 seconds. So over 5. What does that come out as? 7.36 times 10 to the minus 4 volts. All right. So now we have the induced EMF. How do we convert that to our induced current? Well, for that, we just need to, I'm continuing part B on the back of this page. For that, we just need to use our Ohm's law, V equals IR, or as we're thinking about it here, I'm going to rearrange to solve for I over R, right? We just solve for epsilon there, divided by that total resistance 5, that was given. That comes out to 147 times 10 to the minus 4A. We're also asked for the direction. So now we have to do everybody's most favorite part and determine the direction. So I'm going to redraw my picture actually. Just kind of, just quickly like that. Actually, sorry, excuse that one. I'm going to redraw it right here. Those lines are straight. Okay. So as this loop becomes more on an angle, so it's like moving more on an angle like this, what's actually happening is less field is going into the loop. Remember I told you I like to think about it in terms of a cup. So imagine I'm holding a cup open to this way, so the water can just shoot straight in. Someone's aiming a hose, someone's aiming a hose at my cup, and I'm just catching all this water like this. As I move it this way, I start catching less water. As I move it even more this way, I'm catching even less water in there. So the logic that I'm going to apply here is there is less magnetic field going into the loop. So what we need to do by Lenz's law to oppose this is to have more magnetic field going into the loop. To go into the loop, I'm now going to take this circle and put it flat, like rotate it flat. So the magnetic field is going into there. We know the only condition that works is when our fingers are pointing in, our thumb points like this. Therefore, the induced current is in the clockwise direction. So my answer is in amps. I'm going to say clockwise, like that. So I hope that logic made sense. I'm not sure. For me, the cup example makes it easy to see, but I know that's just how my brain works. If there's any doubt in that, speak up, and I'm happy to address that right now. If not, I'm going to move on to the part 3. All right. Number 3. So here we have part of a single rectangular loop. So like I said, like when I read that rectangular loop right there, the sirens in my head go off. I know I'm going to start thinking about, where did I put my equation? Oh, here we go. I know I'm going to start thinking about this. I know I'm going to start thinking about this guy right here. All right. So single rectangular loop with dimensions as shown right here. It's inside a region of uniform magnetic field. The total resistance of the loop is 0.23 ohms. The loop moves with a constant velocity to the right. So we know it's moving to the right. Okay. So the first thing we need to do is find the initial induced current, magnitude, and direction. So I'm going to write part A. Like I said, my sirens are going off. What equation am I using to solve for an induced current? We know we're going to have to solve for an induced EMF. And I'm thinking this equation every day, all day, right? Again, in this case, n equals 1. B is given. L is this one right here. And V, we are given that we're given the how fast it's moving. Uh-oh.
It's good now.
Okay. I just got the 20% alert on my phone. I have an old phone and I've been charging it all day. So hopefully this thing doesn't go down or else we're straight back to PowerPoint, guys. No, I'm joking. Okay, so we're using this equation. The one thing I want to point out is what makes this equation special is that we're not going to be considering area, right? We normally think to use area with these ones, but why don't we? And that's because that these guys and these ones have these equal and opposite magnetic fields acting on them, a magnetic field forces acting on them. So I'll prove that to you later, but for now, just take my word on it. It's going to be this is the length that's being acted on. So we just plug in everything. That comes out at 0.6. I'm sorry. Yeah, 0.6 volts. I don't know why I doubted myself. Gosh, be more confident, huh? And then again, using Ohm's law, except we're looking for an induced current. So I can just plug that in, epsilon over R. We're given that R, 0.6 over 0.23. Comes out as 2.59 amps. All right, we did half of it. Magnitude down. What are we looking at next? Direction. Oh man, direction. The worst, right? So because it is moving out of the page, I'm actually going to pause for a few seconds, let you guys take a 5-second guess into which way you think it go and think about why. Okay. Because this rectangle is moving out of the field, we're going to be having I don't want to say that. How do I say this? We're moving it out of the field. It's going to be consistently decreasing. The amount of field acting within this loop is going to be consistently decreasing, right? The amount of area that's in this field is going to be getting less and less and less as I pull towards to the right. Therefore, by Lenz's law, we want to oppose this. To oppose the less amount of field going in, we need to have more field going in. Therefore, to have more field going in, fingers in the direction of in, thumb pointing this way. I know my eye induced is going to be pointing in the clockwise direction. And all right, A done. Next is what's the initial power? So this is kind of moving in a different direction, but it's meant to represent the multiple equations of power that exist and when to know when to use them. So because the fact is consumed by the resistor, and what do we have? We know we're going to be working with this equation where I induced is going to be plugged in for that I squared value. So plug in what we just got for there. R is given up here. That comes out to be 0. Oh, this comes out to be 1.54 units of power. Bam. All right, letter C. This is the other important question in this one. So, B done. What is the initial net magnetic force, magnitude and direction on the loop? So now we have to go back to a different right-hand rule in which our pointer finger is in the direction of the current. Our middle finger, I apologize, I'm going into the page, but you just gotta trust that my middle finger right here is going into the page. My thumb will point in the direction of the force. So I'm gonna start relative to this bottom portion right here. Finger in the direction of current, it's going, left. Middle finger down, thumb points straight down. Therefore, I have a magnetic force pointing straight down. Let's look at this part right here, where I know the where it's acting as my L value. Middle finger, I'm sorry, pointer finger, middle finger, thumb. And on the top, I have to rotate, sorry. Middle finger, oh my gosh, I keep doing this. Pointer finger, middle finger straight down, thumb pointing up. You have a good eye. This is where I said these will actually cancel out. They're equal, but in opposite directions. Therefore, the only magnetic force that matters is this guy, pointing to the left. So don't even bother solving all of them. What's our equation for this magnetic force? I call this F3 or whatever you want to call it. It equals I L V. Okay. Again, we just solve for I. L, same as above. and then 0.55 for that B constant. And it's going leftward. All right, so now part D. The bar moves with constant, increasing, or decreasing velocity. Well, this one you just gotta take a second to think about it. We know it's moving to the right with some velocity, and this force is causing it to, this force is acting to the left. Therefore, it's like kind of as if something's pulling back on it. So it's gonna be decreasing. And then in part E, the current in the circuit remains constant, increases or decreases. Well, as this value right here goes down, what do you expect? This one will go down too, right? You know, this is the numerator. As this gets smaller, this value gets smaller. Again, decreases. Finally, what is the force required to pull, calculate the force required to pull the loop from the field? Neglect gravity. So what's this force F right here? Well, it just needs to be enough to oppose this. So it'll be 0.5 newtons. So part F, 0.5 newtons, and you're going to be pulling to the right. Remember, this is going to be going at a constant velocity, so to cancel this, F net would want to be equal to 0. All right. Number 3 done. Let's move on to number 4. All right. So for this one, I'm just going to grab my little stencil, draw a circle first, and then I'll explain. Part B here too. Oh, yeah, so here's my circle. And within it, there's a smaller circle, but we'll talk about why in a sec. All right, so here we have a square with a 10 centimeter by 10 centimeter region. And it's so I'm gonna draw it like this, right? My square within there. That square is talking about this one. And has a constant magnetic field pointing into the page. So within it, I have my x's. You have a magical circular loop which can expand, right? So initially it has a diameter of 5 centimeters. So from here to here is 5 centimeters. And then it can expand such the diameter is 10 root 2 in 10 seconds. So 10 root 2 is like, I solved it yesterday, 14 centimeters. So we know that the diameter gets bigger in 10 seconds. So what is the direction of the induced current produced through the wire, if any? Well, we know that the B is increasing going into the page because before the B is only acting within this little loop right here. But then as it gets bigger, the entire magnetic field of this square is acting within, right? Now this circle encompasses all this square which had that magnetic field. So that means there's more B going into the page. By Lenz's law, we want to impose this increase. So that means we're going to need to increase out of the page, right? The only way to have our fingers pointing out is with a counterclockwise induced current. So let me say that again. Here we're initially, by opening up this circle, we are increasing B into the page. We want to oppose this by Lenz's law. Therefore, we need to increase the amount of B field going out of the page, the B induced going out of the page. The only way to do that, to have our fingers pointing out, is our thumb like this, which is counterclockwise, right? So counterclockwise. All right. Now, part B. So the same magical loop then expands to a diameter of 20 centimeters, another 5 seconds. What's the direction of the induced current produced through the wire, if any? So this is where this one gets a little tricky. So I'm going to draw my circles again. Okay. And remember, so now everything's to scale, but I'm going to draw my my box again in here where we know that there's a bunch going in, and this is my 10 root 2 diameter. But now the diameter is 20 centimeters. So this big circle represents my 20 centimeters, right? So it's 20 cm, and this is my 10 root 2 within this little circle. So we ask ourselves, we want to know where's the induced current. The first thing we need to do is wonder about a change in B. Is there a change in B? The answer is no. The reason why is at this point, the circle is already it's already beyond the size of the magnetic field. It can't get more field into it. The circle is at this point, the circle is totally surrounding the magnetic field. No matter how big it gets, it can't get more field into it. Therefore, there is no change in B. By definitions of what we need to have an induced EMF, we need to have a change in B, a change in area in which B is acting, or a change in orientation of the loop. None of those conditions are met. No change in B, that means no induced magnetic field. Therefore, no induced current. So none. All right. One second, I'm just double checking something in my notes, see if there's anything else I wanted to add to that question. All right. Oh, yeah, that's what I was gonna say. I sometimes say induced magnetic field, but that just means magnetic flux. Sorry, I flip those in my head all the time. So yeah, when like this symbol, it's like we're talking about flux. All right. I'm gonna skip number 6. This one's running low on time, and it's not that great of one. But this one is good. This one's hard too. So here we have a power station that is 130 kilometers from Naboo, and it generates power at 30 kilovolts. The two transmission lines each have a resistance of some ohms per kilometer. Naboo uses this amount of power at that voltage. So we want to determine the output voltage of the transformer at the power station in order that the overall efficiency is 98%. You can assume that the transformers are 100% efficient. So those that are acting beyond the power station. So let's first draw out this picture. So I'm going to draw my power station as that symbol. My transformers like this. Here are my resistors. That's a resistor. And this is my city, right? Okay. So there's multiple powers in this situation. Or I'm just going to label, my resistors. Okay. Here's my V at the generator, and then here's the V output. So that's what we're looking for, right? We're determining that output voltage of the transformer at the power station. And we know that these transformers have that overall efficiency that's 98%. So there's power at multiple steps here after each one of these transformers. There's the power acting at the city. I'm just going to call that P prime. We have the power right here. I'm going to call that P1. We have the power before this one, P2. And we have P3. But if you remember what I said, that these transformers are 100% efficient. Therefore, we can say that P prime equals P1, which equals P2. And all those equal the power at the city, which is this guy. Remember, 100% efficient transformers. The next thing I can think is the relationship between P2 and P3. So I know that these two would not be equal. I know that P3 works with a 98% efficiency compared to that initial power sent out. So 0.98 times P3 equals that P2. We want to solve for P3. We already know what P2 is, right? So that just means P2 over that 0.98, plug in everything. P3 comes out to something on this order. Okay. The next thing I should think to find is that power loss as the 98% of transformer, excuse me, P loss by the 98% efficient transformer yields the V out. So I want to find that power that is that efficiency lost, right? So in step 3, I'm going to think P3 minus P2. Okay. That comes out to this value. All right. I want to next pull out current. How should I do that? Well, I'm going to call this P double prime. I'm going to use P double prime, set that equal to that I squared over R total. But our total is a hard thing to find because what we're given here is not actually the total resistance, but a resistance per unit length. So I need to first convert that. How do I convert that? Well, I'm going to need to do some work with my units here, right? So we have this ohms per kilometer. If I multiply that by the total length, which is 130 kilometers, these guys cancel out. And I know it's times 2 because we have 2 transmission lines. So also times 2. At this point, we have enough to plug into this equation so that we can solve for I. So you're going to do some rearranging, where I equals P double prime over R tote. And remember, this is what R tote equals. And then that guy's going to get square rooted. That comes out to be 242.6 amps. All right, so now we're close. The last thing we need to do is solve for the V out. Here, we now know P. So we know we're thinking right here. So we're looking for a current that exists in this part. What's present here? This is part 5. We know P3. We know the current, we just solve for the current, and we want to find V out. Just do some rearranging, equals V out. Solve, V out equals 2.52 times 10 to the 5. Oops, a little bit out, missed that guy right there. Okay, that's how you solve that one. What's important to do is just make the relationships of all the powers at different steps. I know that P prime is equal to P1 is equal to P2. I know that you want to determine the output voltage such that the power station has an overall efficiency of 98%. So I want to plug in that 98 here. We already know what P2 is. Solve. We look for that power that's different between these two positions. We plug that into an equation, and remember to find our total through that unit conversion. At which point you have a current. You can plug your current in here, and you can solve for that V output of the transformer of the power station such that the overall efficiency is 98%. And you can assume that these transformers are 100% efficient, right? Assume the transformers are 100% efficient. All right, I'm going to close this Zoom down. My phone's on like 2%. So I'm going to stop the recording. Thanks for watching, guys. I hope that this new style is better. I saw in the reviews that people didn't, that the PowerPoint wasn't working for certain people, and this probably will make it a little bit easier. I hope it does. Give me some feedback. And thank you for watching. Sign in.